In this video, we will study measuring curvature and radius of curvature derivation. So what is the meaning of curvature? Assume we have this circle and we have another bigger circle. It's clear that this circle has more curvature in comparison with this circle, and therefore we say this circle has big curvature in comparison with the second circle, which has smaller curvature. Let us have this circle, and it has this arc PQ with the length delta S and central angle. We can rotate this arc around the circle and get exactly the same arc. Therefore, we say that the circle has constant curvature. Now the question is how to measure curvature. Let's take the unit circle. It's a circle with radius equal to 1. So this circle has 1 unit curvature, and all curvature are measured relative to this circle. Let's take a circle with radius equal to 2. It's clear that this circle is 2 times less curved than the unit circle. Let's take a circle with radius equal to 3. This circle is 3 times less curved than the unit circle. And if we take a circle with radius equal to half, then this circle is 2 times more curved than the unit circle here. In like manner, if we take a circle with radius 1 over 3, this circle is 3 times more curved than the unit circle. We notice that when the radius of the circle increases, the curvature of each circle is decreasing. And if the radius of the circle is decreasing, the curvature of this circle is increasing. So hence we find that there is inverse relation between the radius of the circle and the curvature. So let us apply the formula. Curvature is 1 over r. So k for the unit circle 1 over 1 is 1, and that is, so the unit circle has 1 unit curvature. For a circle with radius equal to 2, its curvature is 1 over 2, and that's equal to 0.5. And for circle r equal to 3, we get the curvature 0.33. And for other circles in the opposite direction of curvature, we get 2 and 3. Now we can find that we have mathematical description and numerical description of the curvature. In this direction, the curvature is decreasing in numbers, and that's exactly what is happening to these curves. They are decreasing in curvature. And in the opposite side, we have these circles increasing in curvature, and k is increasing in number. And this is the relation. Kappa equal to 1 over r. So the question is, what is the curvature of a straight line? To answer this question, we are going to increase the radius of these circles in order to approach a line. So in such case, we have to increase the radius of the circle and make it infinite. Therefore, when the radius of the circle becomes infinite, kappa will approach 0. And therefore we say that the curvature of straight line is 0. What is the relation between central angle, arc length, and curvature? If we have the circle with central angle phi and arc length s, we have this relation s equal to r times phi. So the arc length s is equal to the radius times the central angle. we can use the centimeter as unit of measurement. So S is measured by centimeter, R is measured by centimeter, and central angle is measured by radian. From this relation, we can infer that the radius of curvature is equal to S over phi. So let's apply this relation. Let's substitute S and phi. We have to transfer this central angle from degrees into radian by multiplying it by pi over 180, and we get the radius of this circle equal to 54.07 centimeters. So let's find the curvature now. Curvature kappa equal to the inverse of r, and that is 1 over 54.07, and the unit is 1 over unit length, or 1 over centimeter. So we can conclude from kappa that this circle is 54 times less curved than the unit circle. So let us keep this equation in mind because we will need it later. Kappa equal to the central angle divided by the arc corresponding to that central angle, and also equal to 1 over r. Assume now that we have a curve C in the Cartesian coordinates, and this curve is not a circle. So the curvature will change from point to point. And the point we are trying to make here is that we have to use the curvature of the circle to measure the curvature at each point on this curve C. So let us start by choosing another point on the curve, P1, and now we have this segment PO, P1. From point PO, we are going to draw a tangent. Phi O is the angle of slope, and this angle is measured positive if it rotates from X to Y. From point P1, we are going to draw another tangent with angle of slope phi 1. From point PO, we are going to draw a perpendicular to the tangent, 90 degrees, and from point P1, we are going to draw another perpendicular to the tangent. These two lines will intersect at this point. From this point, we are going to draw a circle passing from point PO. So this is circle where we call it circle 1. And its radius is R1. Now the problem is we have a point on the curve C, P1, and we have a point at the circle C1, which is F1, and these 2 points are not close to each other. So now let's find this central angle here. We draw a parallel to this tangent line, and we extend this line here. So this is 90 degrees because these two lines are parallel to each other, and since these two lines are parallel to each other, this is the angle phi. Angle phi 1 is exactly the same of angle phi 1 here. The difference between these two angles is phi 1 minus phi O, which is delta phi. And we can find it to be 84.34 degrees. Now, since this angle here is perpendicular to this angle, so both are equal to each other. This is delta phi 1 is equal to this delta phi 1 here. and delta phi 1 is equal to phi 1 minus phi O. We transfer delta phi 1 into radian by multiplying it by pi over 180, and now we need to find the length of this arc, or the approximate length of this arc. So if we measure the arc from point S1, so we have S0 and we have S1, and the length of the arc is delta S1, and this is equal to 118. So we write that down, and now we need to find the approximate curvature at this point, which is the curvature of this circle. So that is K1. We divide delta phi 1 over delta S1 as we have seen before, and we get 1 over 80. So circle C1 is passing from P1, and the curvature of this circle is just an approximation of the curvature of curve C at point PO. And the reason why is because the arc of this circle is not really close to the arc of the curve. So we have to make them closer by choosing or picking another point, P2, and from P2 we draw a tangent, and this tangent is making slope angle phi 2 with axis x, and from this point P2 we are going to draw perpendicular line which will intersect with this line here, and now we have central angle delta phi 2, which is phi 2 minus phi 0. From this point here we are going to draw another circle passing from point PO, and this is circle C2 with radius R2, and we have the point on the circle F2 is now closer to the point at the curve P2. The central angle is 62.82 degrees, and that is delta phi. Now also we measure delta S2, and that is S2 minus S0, and this is equal to 78.38 centimeter. Now the curvature of this circle can be found by dividing delta phi over ds as delta phi over delta s as we did before, and we find it to be 1 over 71. So now we will repeat the same process by choosing another close point to PO, and that is point P3. We draw the tangent and we extend perpendicular, and we get the new center for the new circle C3. The central angle is delta phi 3. From this point we choose this point as the center for the new circle, and we pass it from point PO as we did before, and we get circle C3. We can see now that point P3 over the curve is getting very close to point F3 over the circle. Now they are getting very close to each other, so we have more realistic evaluation of the curvature at point PO. We need two things. We need delta phi and we need the delta s, and we divide them over each other, and we get curvature for circle C3, and that is equal to 1 over 61. Again we choose a point closer to point PO, and that is P4. We draw the tangent and the perpendicular. Now we have the new center of the circle C4. We have the central angle equal to 19.18, and we draw this circle which has this center here passing from point PO, and we find that point P4 and F4 are getting even closer to each other. So delta S4 is the arc length corresponding to the central angle is 15.3. We divide delta phi over delta S, and we get 1/45. Again, we choose a point closer to point PO, and that is point P5. We draw the tangent and the perpendicular to the tangent, and we get a new center for the circle C5. It seems as if it's coinciding with the center of C4, but they are not. And we get the central angle delta phi 5, 6.11 degrees. And this is the circle C5 with radius R5. And now we can see point P5 and F5 are getting even closer. Now the corresponding arc length to the central angle is delta S5. We divide them over each other, and we get the curvature to be 1/46. So let's see if the result of curvature are converging or not. So let's see kappa 1 and then kappa 2, 3, 4, and 5. We can see here that the result of curvature is converging into around 45 or 46. And the closer we get, the more accurate we are going to get the curvature at point PO. We can see that the closer the arc of the curve gets to the arc of the circle, the more the value of curvature is converging. So we can see that if we want to know the approximate curvature at point PO, we have to draw the tangent and choose very close point over the curve, and draw a tangent at this close point, and from these 2 points we have to draw perpendicular over each tangent, and we get the approximate center of the circle of curvature. So here we have 2 points, point over the curve and point over the circle. And we have also central angle, very small central angle delta phi, and very small arc delta S. If we divide them over each other, we are going to get the approximate value of the curvature. So if this point P over the curve gets closer and closer to PO, delta phi over delta S will approach the curvature at this point, will approach the instantaneous curvature at this point. So saying that P approaches PO means that delta S is getting close to 0. And now we have delta phi over delta S approaching the instantaneous curvature. So we can find that K is equal to the limit of delta phi over delta S when delta S approaches 0. Or we can write it as d phi over ds, or the derivative of phi relative to the arc length S. We can see now the direction of a point over the curve when x is increasing. So for each point, let's say -8, we have another corresponding point over the curve, and so on So we can see how this point is moving over the curve when the independent variable x is increasing. So let us investigate the curvature sign. We have case 1, 2, 3, and 4. How do we classify these 4 cases? By realizing that y could either be increasing or decreasing when the independent variable x is increasing, and by realizing that the curve could be concaved down or concaved up, or concaved in the negative direction of y-axis or concaved in the positive direction of y-axis. For case A, we find that phi 2 minus phi 1 is negative, so kappa is negative. For case B, we find that phi 2 minus phi 1 is also negative, so kappa is negative. For case C, phi 2 minus phi 1 is positive, so kappa is positive. And for case D, phi 2 minus phi 1 is positive, so kappa is positive. Now we conclude the criteria for curvature sign. If the curve is concaved in the negative direction of y-axis, then kappa is negative, and if the curve is concaved in the positive direction of y-axis, then the curvature is positive. We also notice that the unit tangential vector here, if it is rotating from y to x, then kappa is negative, and in the second case, if the unit vector is rotating from x to y, then the curvature is positive. Let's find out now the curvature formula in Cartesian coordinates. For a curve giving as y equal to yx, we also assume that this function exists, and we remember the following formulas: the definition of kappa, and the derivative of s relative to x as the tangent of phi equal to dy over dx. If x changes, then phi will change and tan phi will change. We call tan phi function f. So that implies we have two functions, function phi and function f. And they can be written as nested functions. So if we want to derive function f relative to x, we use the chain rule, and then we substitute the derivation of tan phi here, and we substitute tan phi here, which is dy over dx, and again we substitute tan phi with dy over dx, and we get this relation here, which is important for us. If x changes, then the arc length will change and the slope angle will change. So we have here two functions, s equal to sx and phi equal to phi s. We can write them as nested functions, and if we want to derive phi relative to x, then we use the chain rule, and then realizing that ds over dx is this square here, so we substitute that, and d phi over ds is kappa, the curvature, we arrive at this equation here. So we arrive at two important formulas, this formula and this formula, and they have something in common, and that is d phi over dx. So we substitute this formula here, and we get a formula with kappa and the derivative of y's relative to x only, and that's exactly what we need. So we solve for kappa and we get this formula for kappa, and the inverse of kappa is the radius of curvature. So let us find the radius of curvature of the curve y equal x square. First we find the first derivative, and after that the second derivative. We substitute in the radius of curvature formula and we get this relation. So at point x equal to 0, we get r0, radius of curvature, at point 0 equal to 0.5. So we draw the radius and the circle of curvature here, and we do that again for x equal to 0.5. So at this 0.5 we have radius 1.4 perpendicular to the tangent at this point, and this is the radius of curvature. We do that at point x equal 0.75, and we draw the corresponding circle of curvature, and again for x equal to 1. Now the radius is increasing, so it's 5.59. So at this point 1 we have this circle of curvature. Thank you for listening and have a nice day.